Swayam Prabha. Digital India. Educated India.
We will be continuing this slope stability improvement using geosynthetics or any other suitable form of reinforcement in this lecture. And as I just mentioned, we have a simple method in which if you know the required reinforcement force in terms of the coefficient k. As I just mentioned, we say in the case of a retaining wall which is vertical, Ka gamma h square by 2 will be the force, and Ka can be calculated in terms of this like 1 minus sin phi by 1 plus sin phi, something like that. And if you know the inclination, it can be found out. And if there is some, if there is an earthquake that comes, one can even calculate what is the earth pressure increment, dynamic earth pressure increment also one can calculate. So this concept is very important in terms of understanding what is the required earthquake, what is the resistance required to really see that it can sustain some horizontal force, either it is in the form of lateral pressure from its own weight, or because of its the earthquake, or it's because of the seepage forces and all that. So this design charts that are developed, of course there are many design charts developed in these lines, but I find that the Jewel charts are much elegant to use and simple to understand. And as I just mentioned, we try to calculate the required force, and also what is the length now. Length is something that, like, so it is very important to understand that, as I just mentioned in the previous class, that if you know that length of the reinforcement, the height is say 10 meters, 0.7 times will be the length of the reinforcement. So that is about vertical, and that is just a preliminary guideline. And say for example, you can see that the same thing also comes here, like if the wall is vertical and if the friction angle is say for example, if it is 20 degrees, it is 0.8 times the length of the reinforcement. If the friction angle is 20 degrees, is 0.8 times. Okay. Similarly, if it is 25, it is like this, and it is about maybe 0.63 or something like that. Okay. So these things will give you some idea of what should be the length of the reinforcement required for overall stability. Okay. This is the length required for overall stability, and this is the minimum length required from direct sliding considerations. You can see here that if the slope angle is about 90 degrees, and if it is phi equal to 20 degrees, it is about 0.6 here, like if it is 25, it is 0.438 here or something, but you have to take whichever is higher. Okay. So they have assumed some sort of failure mechanism. The basis of this is that they have assumed some sort of failure mechanism. It can be in the form of a log spiral, or it can be to calculate earth pressure coefficients, you have to make some assumptions. Okay. One can use a log spiral failure mechanisms, one can use a wedge mechanism, or one can make a two-part wedge, like it will have two wedges, because it is much more close to what people have observed in the field. Like why these failure mechanisms are assumed is that some of these failure mechanisms are noted when you see that there is a failure. So when the retaining wall failure is there, there is a sort of a logarithmic parabola or whatever, it can be a logarithmic spiral, some sort of failure mechanism is there, and that is the reason to calculate that forces that are acting on the retaining walls, or even in slopes, we try to calculate this earth pressures. So you can see that based on the combination of these three diagrams, one can calculate the length of the reinforcement and also the the required force, that we will see with an example that will be much clear. So, the first figure in the chart that I just presented gives the earth pressure coefficient K required, which is the required reinforcement force for equilibrium to be calculated. The second two figures in the chart gives a minimum required length Lr by h. The minimum required reinforcement satisfies both internal and overall stability requirements and prevents direct sliding through the reinforcement block. So, what we do actually we will have to assume number of failure surfaces and finally try to come out with this number, and already it is internally done in this particular method. And how do you use these charts is something that I would like to illustrate in the form of a simple example. You have, for us to help values from the charts, you need to construct what is the maximum required stress in the soil, like what is the, say for example, the thing is Ka gamma h will be the stress at any point, is it not? If you can, as that is called the line envelope or line of maximum required stress in the soil. Then locus of minimum available stress from the reinforcement. What is that the reinforcement is giving? See, you know something is required, like the earth pressure at any point is calculated in terms of Ka gamma h. But what is it that the reinforcement can give? If it is very stiff reinforcement, it can give inward shear stresses and it can be little stiffer. So, it will, what is available is that, and there is also a surcharge and all other things are also there, even one can consider some of these things in some design. Suppose the vertical, the slope, it has some traffic load at the top. How do you consider that in the design, right? That also should be addressed. We will see that. So, first thing is the construction of envelope of maximum required stress in the soil. The basic required stress for equilibrium is determined from the depth below the z, and we know that it is Ka gamma h type of thing, where sigma required equal to gamma d is nothing but gamma b is in terms of design. D is a term that denotes design. Like what happens, as I just mentioned, you may have a number of density values, like from backfill, and you should choose some number which is a basis for design. So, that we say is gamma d. Then z is any depth and K is a required coefficient. So, at any depth the required stress is nothing but gamma d into z into K required. And as I just mentioned, if you remember, that calculate the bond resistance and increase in the earth pressure coefficient. If you remember, I just mentioned that there are two things which will decide the effect of reinforcement. Actually, I just mentioned that if this is a failure surface and you try to provide a reinforcement like this, and I was mentioning that if you place the reinforcement in the direction of principal the tensile strains, okay. If there are some tensile strains in this direction, if you place the reinforcement, the tensile strains will be very, the reinforcement will be very effective. If there are not, if there is a compression, you put a reinforcement, it is not useful, okay. It is as simple as that. And if there is some, what happens when I just said there is a sliding that is occurring in reinforced soil, take one element, we discussed this in the class, take one element on the failure surface, and when it is subjected to shear, some part of it is subjected to a tension and the other part is subjected to compression. In the direction of shear, it's there is a tendency for elongation, and assuming shear and tension is there, they are all together. So, you try to put the reinforcement in this same direction. We have seen the reinforced soil principle, where if you place the reinforcement in the direction of tensile strength is maximum. That is one consideration, okay. And we also discussed that the to get the maximum effect in the reinforcement, the 45 minus 5 by 2, that we discussed, 45 plus 5 by 2 will be the angle at which it will be very appropriate. We have plotted a diagram in which the orientation effect is there, and then you try to calculate the delta shear force that comes from reinforcement. We saw that at a particular angle they are all optimum or maximum. So, that is one thing we have seen, and in terms of, there are two important things for reinforced soil to be effective. One is called tensile force mobilization, the other one is bond resistance. Okay. The bond resistance point of view, the orientation of reinforcement should be like, if there is a vertical load applied and if the reinforcement is like this, you can't pull out. So, the direction of bond stress is like that, and the direction of reinforcement is like that. So, the angle is 90 degrees. So, to get the maximum benefit due to bond, you have to place the reinforcement at 90 degrees to normal stress, that is one thing. Whereas, in the case of tensile force mobilization, if you put the reinforcement in the direction of tensile strains, you will get the maximum effect. So, the direction of the placement of reinforcement, in one case it is 90 degrees from bond, in the other case it is 90 degrees in terms of the 0 degrees in the case of tensile reinforcement, and most of the time what happens is that, as I just mentioned, it will be at an angle. So, so that small correction has to be applied, see, that is what I was trying to mention here. Like all these earth pressures, we assume that it is total force acting on, you are calculating the K required based on this, but the K required will be little higher, it should be little higher. Why? Because the reinforcement, this is not the force in which it is acting, and the reinforcement is at some inclination with reference to the failure surface. So, to make that correction, we have to use a factor called 1 minus LB by LR and increase the design earth pressure coefficient. Then calculate the critical depth to determine the minimum required stress at the crest of the slope, make allowances for surcharge, compaction, other forces, that we will see. Like surcharge is nothing but one, like traffic loading, then compaction, because you will be doing the rolling using equipment, and there will be earthquake forces, seepage forces and all that. Okay. What I want to show you is that this is what I meant. This is the force, this is actually the reinforcement slope at an angle beta, and this one is that if I just take it as Ka gamma h, it will be like this, K required, this is, it will be like this, is it not? But so if you just calculate the reinforcement based on this, actually how do you calculate reinforcement force? It is nothing but K required into gamma h into SV into SH, as simple as that. You have some space, vertical spacing and horizontal spacing in the case of some reinforcement elements. So, that is the tensile force that mobilized, or that is likely to mobilize. So, what we should do is that is we assume that its whole force is acting, but there is some small changes here that there is a second one, which is nothing but there is some from bond and reinforcement angle considerations, there is a small correction factor you have to put in. So, because of which the required reinforcement force will be little higher. Then at the top, actually you are trying to do the compaction, actually in every layer we do the compaction, but what happens is that the compaction stresses will be much, see the Warden pressure stress is very high, see what happens during the process of compaction, we will have some sort of pre-stress induced into the system. So, that compaction could be, say for example, I am just mentioning it here, like gamma b into say depth is something, say for example, it is 18 into 1 meter is one value, and 18 into 2 meters is something like, it follows like this, 18 into 2 meters, 18 into 3 meters or something like that, it follows this line. But at the top it is 0, but practically it is not 0. Why? Because you have compacted it, and there is always some sort of earth pressure for which it is to be designed, because earth pressure is never 0 at the top, and you have allowed compaction static. Actually we do not really compact, we use some sort of simple compaction equipment like hand held equipments are there, we just do some compaction here, whatever there is some compaction stress induced, and to resist that compaction stress you should have a reinforcement. Okay. So, up to this point it is just that it is Ka into Ka into gamma h into SV into SH will be that force, and as you come up, as the depth is less here and it should not go here, because that you will have some stress because of the compaction, okay, that you should take here, and then you should design that this is what is called required stress in the reinforcement. Okay. So, this is that minimum value, actually minimum value because of compaction and other things that we have, and after that it is like this. So, see, you may have a general impression that if you put there is no pressure here, there is no need for reinforcement. It is not correct. Why? Because there is a pressure because of the earthquake, the earth compaction, right. So, that is very important, and not only that, suppose you have a surcharge here, you have some traffic. Now, this is just a slope which does not have any surcharge, there will be some lateral pressures also here. So, to keep that in the stable condition, we need to have some sort of reinforcement here as well. So, that is what I want to say. So, we normally try to come out with some sort of reinforcement, the locus of minimum available stress from the reinforcement. We try to devise a reinforcement layout so that the minimum available stress at every depth exceeds the envelope of maximum required stress. Actually, what we did in the previous case was that this is that required stress, and you come out with a reinforcement diagram which is like this, where the stress in the reinforcement is always more than the required stress. That way you ensure that it is stable at all levels. We will see that anyhow. And available stress PAV is nothing but this is SV into SH, that depends on both the reinforcement force and spacing, and you can always meddle with the spacing and length and all that. Of course, if you are using a geogrid or a geotextile, its horizontal spacing is per meter length. Actually, there is nothing like you can change any spacing, but if you are doing some nailing and other things, one can have some suitable horizontal spacing of half meter, 1 meter and whatever 0.75, you can change it. So, you try to see that the available stress in the reinforcement, say the allowable, this is what you are going to get from the company. The available stress should be more than the required stress, that is what we do. Suppose you take some reinforcement bar in nailing, you can always say that allowable force into SV into SH should be more than the required stress. If you are able to do that, it is fine, job is done. That is what I am trying to show here. This is the available stress in the reinforcement, okay. This is what I showed you just now, and sometimes our objective is to place now reinforcement, okay. So, you place reinforcement like this and you try to calculate, see there are two zones here. In fact, what you are trying to do is that one way is that you calculate and put a one single type of reinforcement which is like this is the lowest zone, because sometimes what happens if the depth is shallow, say for example 5 to 6 meters, it is okay, but if the depth is say 10 meters or something, it is or 7 meters, it is better to choose two types of reinforcement so that you do not really waste the material. What happens is that this is a lower zone, lowest zone stress, where P allowable divided by SV into SH is nothing but this one type, and here you select such a manner that this is one, and then the second one also you try to choose in such a manner this is available stress in the second zone. So, actually suppose you are using the same reinforcement everywhere, what happens is that you will have a vertical line here, and this is required, this is available, extra available. So, you are not utilizing it properly. Say for example, this is say for example, this could be some number here, and the available force in the reinforcement is so much, which means that you have taken a very good grade of geogrid or something. So, this is underutilized, right. So, what we do is, and at some point depending on the availability of the material, we will try to choose some material which is something better, but then it can be a cheaper cost, cheaper and less strong compared to the previous one. So, this way you can really understand this whole concept and see that at any stress level you try to keep the reinforcement satisfactory, and in the sense that limit, like always the available stress in the reinforcement should be more than the required stress. Okay. Now, it is an example. You are trying to design an 8-meter slope with an angle of 80 degrees, it is nearly vertical, you can see that, with a 15 meters wide, maybe you are trying to have a car parking or something, road widening work, like say for example, you have a narrow area here, you would like to increase the road width. So, you 15 meters this side and 80 meters slope you can make, in fact that is what we people have been doing elsewhere. And now you have a granular fill you are taking, and design values, okay, you may have lot of values for the same material, but you take 21 as a design value, friction angle as 31 degrees. Okay. Now, design assuming zero surcharge and pore pressure. Okay. So, surcharge is not there, and pore pressure coefficient is also 0. These two things are very important actually. You have a simple equation to say, for example, if there is some surcharge applied, you can convert into an equivalent height actually. So, if there is some 8 meters is what you have, suppose somebody says that I have a 20 kPa as a load, then the way that we get the equivalent height is that you can, the thing is that you have to get the equivalent height by considering that extra 20 kPa as load, and also its unit weight of that soil. So, once you do that, you will get that equivalent height, like nothing but it is like Q is 20 kPa, Q divided by then the bulk density, say for example 18, 20 by 18 will give you the extra height, say 1.1 or whatever. So, when you have a surcharge, you assume that it is only 8 meter slope, but design it for 8 plus 1.1, okay. That surcharge effect is considered, okay, and like that. So, design in this case example I am just only illustrating, but suppose you have a problem with surcharge, particularly when you are trying to design using IRC and other guidelines, you need to know how do you handle surcharge, okay. The required design life is 60 years, okay. Then the design conditions are TD equal to 60 years, and the design temperature is 20 degrees, okay. These are all some, these are all that you get from a geocentric company, and the reinforcement grids and index properties in the range of 110 to 135 are available. Like you have number of companies nowadays in India and abroad, where you get index strengths varying from quite big, if you are going for geocentric the slope applications, there is so much range they will come and give you, even geocentrics can be there. Then as I just mentioned, the coefficient of skin friction for this geogrids is 0.6, and they will have a similar geometry with alpha s equal to 0.4 and s alpha b equal to 20. In fact, I was just I need to mention that these are all required in the case of calculation of bond resistance, and the objective is to design a suitable reinforcement layout, right, suitable reinforcement layout, and you try to come out with you have some geogrids and all that materials, and there is some loading and everything is given. How do you come out with suitable reinforcement force is a question. What is available here is that now you are designing it, say for example 50 years or 60 years, and room temperature is also given. The companies know they will give in this form, okay. Index strength is say 110, 80, 55, 35, they are all called reference strength. It is called characteristic strength and reference strength from the manufacturer. Then they have, as I just mentioned, there are some finally you need to apply this character, the partial factors such as FD damage factor 1.2, 1.1 and 1.5 for one log cycle of extrapolation. So, once you do that, you have it comes to 66, then if you want to correct it for damage and other factors 50, then finally it comes to 33. What it means is that with all the 110 divided by some of these factors will lead to this number 33, okay. Though this is a reference strength, you have a factor of safety of 110 divided by 33, okay. All these partial factors whatever you choose will be forming that number, and so what you are allowing is only 33, because as I said it is for 60 years, right. 60 at the end of 60 years also it should it should work for 60 years, okay, that is the assumption. So, we at the end of 60 years we expect that this is the force that it comes down. So, we assume that we design for this, actually we assume that this is a design force, design allowable force, and for 80 grade 24, 55 it becomes 16.5. You have 4 varieties actually, because why we have 4 varieties is that you can optimize, as I just showed you, that one can optimize the length of the not length, at least the spacing, and also the quality, each could be expensive. Say this may be very expensive compared to this last one, like that. So, once you have all these factors, these are all the important numbers now. Once you know this, normally this will be given by manufacturers, and all these things you should get from the manufacturer literature, and even in fact one should do tests also. Like say for example, if somebody says that 1 ton is index strength, you have to measure in the lab using a tensile. We showed you, we discussed various types of tests one should do, and we have seen that these things are very important in quality control, and we also should check out with some of these the factors. In fact, as just mentioned, the tensile strength reduces with time. I showed you the diagram. Okay. So, tensile strength reduces with time, and if it is say if you test for 1 hour, there is a test actually where you test immediately and test for a few, like 10,000, I mean, like it is at least at the end of 42 days also. It can be, people can continue the test and then take the samples and then measure them, measure the test, get the values, and one should understand that, and then they extrapolate actually. Okay. If you have say for 1 day and 10 days, it can be extrapolated to 100 days, like 1 and 10 and 100, they constitute a log cycle, 100 days, 1000 days, like that. One can extrapolate, because you simply extend that horizontal line, the line in the log sheet actually. Okay. So, what are you trying to do is that, so I will show you how do you go about this design. Obtain the basic required earth pressure coefficient 0.23 and the required reinforcement length. I just showed you the previous diagram, like that chart. Okay. Based on the 80 degrees inclination and friction angle of this this thing, you will get this required. If you remember, I just mentioned that if it is vertical and phi is 30 degrees, it is 0.3 or something like that. It is little less here now, like maybe its slope angle is 80 degrees. So, required is 0.23, and we also see the charts for the same thing, and 0.53 and 0.28 for the design charts for Ru equal to 0, beta equal to 80 and phi equal to 31. Okay. Slope angle is little higher. So, what it means is that whichever is higher, like 0.53 and 0.28, we should take the reinforcement length. So, the reinforcement length will be 0.53 into 8. 8 meters is the height, is a 4.3. So, length of the reinforcement is 4.3. So, suppose you do for a surcharge, surcharge is there about 20 kPa. What you should do is that here you should just everything is because these are all in terms of LR by H, there is no problem here, but then here you have to make it as 9.1 or something, depends whatever extra height you will get here. So, that length you have to provide, right. So, now what we do is that we provide some spacing of those materials for a constant spacing of SV equal to 0.5 meters throughout the slope. The maximum required stress at the base of the slope is like K required is what you have already got the number, K required is some 0.23, and H and all that you get on 0.39 you get at the bottom. The grid reinforcement in the index strength is 80 is selected for the lowest reinforcement zone, as it provides a minimum allowable strength. Say for example, I have given you those diagrams, and 24 is allowable, right. For one of the materials it has 24, 24 divided by 0.5 will give you 48. So, consider one more thing, as just mentioning, this is 24 is nothing but the material property 80 has been reduced to allowable force, 24 divided by, now this 0.5 is the spacing. So, 48 is the allowable force required. So, considering bond resistance 1 minus LB by LR, this is another one. The other one is that there is a calculation required for LB also, and LR we have already got that length as say 5.3 in the previous diagram. LR is 4.3 meters, and LB is, we have another expression. Finally, it will be always less than the 1. So, you get this term called 0.94, and this gives, now as I just mentioned, this reinforcement coefficient like 0.23, which was there, which we obtained in the previous step, should be little corrected, and this will become 0.24. Essentially, as I just mentioned, that this is because of the orientation effects. Okay. Orientation, as I just mentioned, tension, the reinforcement should be placed in the direction of tensile strains for the maximum benefit, and for the bond it should be placed in the at 90 degrees to the vertical stress. But in the field condition, there is an intermediate angle, and because of which the K required has to be corrected, it has to be increased actually. And for LB by LR equal to 0.06, the minimum required, there is another computation that we have, and we have another step that actually this given in my book, and LB by LR is 0.06, the minimum required stress is sigma minimum is 2.2. Like as I said, at the top also you have some minimum stress, okay. Like as I said, it cannot be 0. You have to have, if you are simply placing with hand and other things, minimum stress, but if you have compacting, it can be much higher, like it can be 100 kPa. Now, what you have is about 2.2 kPa, which is very small number. Okay. So, what we did was that we just have this correction, which we have the required stress and like minimum value, this is about 2.2, and this is a slope angle, and assume that you are using some compaction and all that. So, it may have the required stress could be little here, like how do you get that thing? One can also do, what you do is that it's a sandy material only, and you do a sort of a consolidation, E log P curve for that, and then there is a you can draw the tangents from either sides, and then there is an intercept you get, and then it could maybe correspond to 100 kPa. If you remember, I showed in the case of compaction chapter the amount of pre-stress that the materials have. For example, in the case of clays, there is lot of pre-stress in the clays, but in the case of sands it could be lower. So, that pre-stress value one can get from here, and maybe make it with some correction and then use it here, and to get, if you are using compaction. If you are not compacting, it is fine, you need some minimum stress because of the bond considerations. Okay. So, this is K required and K design, and then minimum stress values. Now, suppose you are going for a single reinforcement layer throughout that 8 meters level. The allowable 24 by 24 is that, and then 0.5 you have 16 layers, right, at every 0.5 meters. Actually, the thickness, why is it 0.5? In fact, as I just mentioned in the compaction class, that the density within this 0.5 should be same and constant, and it should give very good strength, and also it should give very good resistance between the soil and reinforcement. This is very important. And so, when you take P allowable as 24 and spacing as 0.5, the number of layers will be 16. In some case, as I said, you have other two materials also. I said just 10.5 is one thing, and you can also use, where at the top, because you may not have lot of stress at the top, you may have a weaker material that one can use with the same spacing, and also intermediate one 16.5, one can see that it can also be used. I will just show you the diagram. What it means is that this, if you are using this depth versus the required available stress, required and available stress, this is what is required and this is what is available. You can see that 48 kilonewtons is available. Maybe it is fine here up to some level, right, up to some level, but you can see that it is all wasted here. Okay. If you use a very good material like with 24 kilonewtons, it is not worth having 16 layers, it is underutilized. So, what we do is that one way is that you take 10.5 kilonewton one and then have spacing, and you can put up to some layers wherever it comes in. See that the important point is that the available stress should be more than the required stress. Up to this point you can go, and you keep at the top you can only keep this 10.51, and then this at this all these points it is fine, but once you come here you try to go for a higher one. So, you are able to effectively use your material in some sense with just replacing the good material with a somewhat weaker one at the top, but here you have much more better configuration here. 8 meters is there, and say you do not need to, you also have one more geogrid material which is in between also, like you have 3 materials, one is 24, one is 16.5, one is 10.5, and try to maintain the spacing. Actually we do not meddle with spacing too much unless it is required or when it is very useful, because it sometimes from construction point of view it is much better, and particularly in small slopes, like, so you can see that all at 0.5, 0.5, 0.5 you can provide, and this is the required stress, and allowable stress you can see that okay, at this point little extra, it is fine, it is this thing is little extra, it is fine. At every point you see that all available stresses are more than the required stresses. So, it is very useful to say that the design is also like the way that we calculated was that we also had directly the factors of safety, because we got these numbers based on that time and other extrapolation numbers, damage effects and all that. What was some number, it became we have considerably reduced those numbers and got the design. So, this is the length of the reinforcement required, this is the spacing required, and this is the type of geogrid required. This is what the answer is. Answer for the question is that if you want to say that, if I want to say that this is the suitable reinforcement configuration, yes, this is that. What you got in the process was that, like you had 3 materials like 80 kilonewtons, 55 and 35, and assume that relative unit costs maybe 543, like this could be maybe 5, say in Indian currency I can say 500 rupees, this could be 400 rupees, it can be 300 rupees, right. So, like some units like 5 units, like it could be say $10, it could be $8, it could be $6 or whatever. So, when you say that, and in the design 1 you have 16 layers, and the relative cost is 80, okay, because 16 into 5, right, 16 into 5 is 80. The second configuration that we discussed, it 10 into 6, it is 68, and you are going for the third one where you have all the 3 things like so you have 5, 6, 6, it is 63. Even within that geosynthetic material, normally see what you did, 80 meters is definitely unstable, you do not get any factor of safety, is definitely is less than 1, and you use as reinforcement, geogrid reinforcement, and actually these reinforcement charts that I just showed you are based on some the design coefficient of 0.8, So, even using that you are able to get with a wiser choice of reinforcement, you are able to get 20%, about 21% savings over the design 1. What I want to say is that one can do a very systematic analysis. In fact, this design charts are simple tools, but one can do rigorous analysis and come out with wonderful this thing, and this is a typical slope actually. See, in fact, 8 meters is one, but but suppose you want to go for say 40 meters. In fact, the highest the recent about sometime back I visited two reinforced at slopes. One is 22 meters high, which is very good, which is doing very well, and but then I visited another one which is supposed to be 42 meter high, which is supposed to be very high in one of the highest walls, and but it had some problems because the field engineers have not understood the behavior of reinforced soil well, soil walls or soil slopes very well, and you can see that when it can be even tired construction, we call it, it can be, see, you can just put in terms of tires and then construct. This is a highway, and one can do a sort of, instead of a regular retaining wall, one can construct this. So, this is another one that one can have in any type of diagrams, and this is what type of finishes one can have. This is another interesting example, and you have see all could be pathways, and it can be blended into our aesthetic design very well. This is another example. Of course, actually we have so many companies in India and abroad that if you just visit their home pages, there are so many companies. This is one case with one company called McCaffrey, in which they supply this sort of reinforcement, and you put some gabions like this and all that, and you can construct. This is the reinforcement system, reinforcement system, and you say that whatever is you can design this, you can specify, and then the company may have standard designs. What happens is that when the companies may have standard designs, it's our objective as a designer is to cross check the design, because the designs are sometimes not foolproof, and there could be some unusual situations where the designs can go wrong. So, in fact, what I saw in the particular RE wall, RE slope in the other place called Vijayawada, where they could estimate the deformations of the slopes properly. That was a big issue. Now it is somewhat stable, but it has really been a bit problem in reinforced soil slopes, because the height is 42 meters, which is one of the, it's not a small height, and it is also on the curvature. There are many design issues, and this is another example that one can have here. See, this is a reinforced soil slope. It could be about 70 degrees. This you can see that this is also about very high slope. It's not easy, right? So, one can, the beauty with this, some of the systems is that you can also allow the vegetation to grow up. In nice terraced slopes, it can be very nice, and it can be like this, as good as this. If you just in the beginning itself you construct and then put some sort of nice plants that can come, and it can be as rich green like this, and it is very useful. This is another case study, of course, from some other company. There are many case studies that one can do, and like this is another type of construction that people have. Okay. And this is again, it's simple. You can see even the construction that they are doing here, like normally, like you have a reinforcement, and then on the reinforcement you have a backfill being spread, and then it should be rolled and compacted. As I just mentioned, it should have a good densities, right? It should have good density because see the objective is that it should have very good friction between the soil and reinforcement, and there should be a very good drainage actually, because what I just showed you was that the drainage is very important. Okay, you have I gave you the slope design for RE equal to 0, where the pore pressure coefficient is 0, but if there are seepage pressures or some horizontal force, what happens is that earthquake force or even the length of the reinforcement will be high. Length of the reinforcement required, as I said, it could be say 0.7 times height, or some, you saw, depending on the length of the reinforcement, what should be the depending on the slope angle and the phi friction angle of the soil, what should be the angle you can get, but it also should account for the seepage conditions, like if there is a saturated condition, or if there are some pore pressures, you should have. Say for example, in a hilly area, if there is some water always coming, then it is not, so you should possibly put proper drainage and see that the water is removed, and also the length should be adequate. In such case what happens, if the length is not adequate, then it fails. In fact, in many places in abroad, like in Vietnam and other places, because of not providing adequate length, the reinforced slopes and walls have failed. And even in India, there are many cases where if they do not understand the principles of reinforced soil wall well, or reinforced slopes well, then they are in for trouble. But then it is a very efficient technique, where you can see that where you can't construct a 70-degree slope, but because of this technique it is possible to construct, right. So this is a typical backfilling operation. This is about facing elements and all that. One can do all these things, many things are possible. Okay. Then so this way they construct, and this is also some case studies we have. And in fact, if you just go to, actually as I just mentioned, if you remember in the first class, Henry Vidal was the discoverer of the reinforced soil technique, and the first applications of reinforced soil technique are in slopes, particularly in France, and they have been very effective. And people have, even in Himalayas you see land, you have a lot of slopes like this, and in many places people have been doing it very effectively, because the thing is that particularly in hilly areas you want to extra widen the road, and but so you have to start from bottom and have some, say suppose you want to increase to say 10 meters, you can identify the area and see that it is okay, and try to find out the backfill material, try to give a design, and it is possible, that is very important. And this can be done, this type of facing, any type of materials can be used. What I want to just say is that this reinforcement of slopes is a viable technique, particularly in as I just mentioned, the design of slopes, it is very important. And the design philosophy has been very simple, right. Design philosophy, in fact I must tell you, there are so many guidelines on this, so many software are there, online software and commercial software, and company software also. So for example, if you are using a particular company, they have their own, the thing is that they will only make geogrades of certain grades, like say they may use one material only, like say for example as I just mentioned, you have different types of geogrades, you have different types of geotextiles. So yeah, you also saw in the same example, like it has a tensile strength of 80 and something like that. So some of these people, what they do is that to make all the process easy, they just make it customized to their own needs, to they would have had their own labs, each company will have their own labs and all that, to find out the tensile properties, drainage properties, friction properties, and all that, whatever is required in design. Like as I said, even many things, they just even damage factors, if I was just mentioning about the damage factors and environmental factors, all should be calculated. The companies will have all that information, and once you have that information, then it is very easy, in the sense that you have to use appropriate software and do that. And actually see, the method is also quite simple. You have seen that you are trying to calculate what is the driving force and what should be the resistance that is to be available, and if the resistance is not available, you are trying to increase that by a suitable factor of one suitable factor. In fact, this factor of safety is another big problem. I want to tell you that I see this in slopes, if you have less factor of safety, say for example 1.3 and 1.4 or whatever, it means that there will be some deformation. In fact, many people have not been able to appreciate that there is a friction between the soil and reinforcement, because of which there will be some deformations. And if there will be, if you do not understand that there will be deformations, then and so for example in some wall, which I saw, so for example some Vizag or some place, it is say 10 meters high wall, there will be some 0.01% will be the deformations. So, if there is some deformation of some 5 mm or 10 mm are expected, it will happen, and if you think that because it is a structure, compacted soil structure, there will be some deformations. So, like literature says about 0.1%. In one case what happened was that the height of the retaining wall was about it is a slope, it is about 42 meters, and if you take about 0.1%, it is about 420 mm actually. So, 420 mm is a big number, this much. So, 40 mm, so if you construct that wall, it is bound to settle by that much amount, and these people what they did was that they have just placed everything, they constructed the RE wall and started pouring the concrete on the top. They want to construct the road, but then the road cracked, in the sense that 420 mm is a total settlement expected, and there will be some changes also. The PCC cannot take tensile strains, right? Pre-stressed that plain concrete cannot take, it is not reinforced concrete also, like they started some simple paving block or something they started putting, and what happened was that it was settling, and they kept on adding, they are trying to put layer by layer cement and all that, which was not necessary, and finally they were very alarmed that there were a lot of cracks, but the fact was that they did not understand, it is the deformations of the reinforced soil have to be expected, because it is a I said the compatibility between reinforcement and soil is there, and to make sure that the compatibility works, there will be small deformations, and that lead to that much thing, and if the wall height is going to be higher, it is definitely have this thing. So, that is very important, and see many of these techniques could be used for repair of failed slopes also, as I just showed you in the beginning, like there is a slope failure, and how do you repair it. So, in that point what happened, maybe the area everything was fine, but only at that point there is some problem where because the driving forces are more than the resisting forces. So, you can do nailing there only. So, for example, nailing, some places you do not need everywhere, the thing is wherever it is weak you have to strengthen that place. So, one can really even use the same design philosophy, of course we will discuss this much more in detail, but essentially one can evaluate some of these factors very well using this reinforced soil technique very usefully, and drainage is very important, because you have to, I have seen where particularly these techniques are useful in slopes, and slopes there will be lot of water coming up. So, you have to provide drainage layers even before constructing, and the other important point was that there is some native soil will be there, and you are putting a backfill, and between the backfill and the native soil you have to have some sort of connections, because what happens, this is a new material somewhat it will be the stiffness will be different from the stiffness of the native soil. Okay. Native soil has some stiffness. So, for example, there will be a fractured rock and you are trying to put a backfill here. So, the stiffness of the fractured rock is different, and the this thing the backfill is different. So, you need to have some sort of interface connections between the native soil and the native rock and the soil. In fact, if you just see in Vizag, they have Vijayawada, they have shear connectors, just transfer the, if there is some integrity somewhat maintained, otherwise at the interface should not be a cause for failure, it should not just whole thing should not come out. At the interface shear resistance between two interfaces like native rock and soil, there should be some intersect, and then if it tends to fail, that length, that area of cross section should be sufficient, and to see that shear will not occur. So, this is very important, and I am sure that this needs much more, a lot of research is being done on these lines, both on experimental side, numerical side, and in the field studies, like people have been doing this, there are so many issues in this. Thank you.